Yep, now we can.
Okay. So last week we covered the NOT gate, and the NOT gate was the first gate we covered, and it's similar to the classical NOT gate. So it flips one state from its, let's say, get state 0 to get state 1, and we said it's an identity matrix. Yeah. So today we are going to cover the Hadamand gate, and this is the first quantum gate. So it creates an equal superposition state of a given computational basis. So this gate contains quantum capability compared to the NOT gate. So it's denoted by capital H, and it turns the state 0 to this. It would be good on a computer, but there's this equation. So it turns it from get state 0 to this state. Then when we apply it to 1, we get the same equation, but there's a minus sign. Yeah, so those are just states, but it can also be applied to a superposition. So this is the equation: alpha ket 0 plus beta ket 1. So alpha can represent a complex number, and beta. So it turns them into this state. This looks a bit untidy, but that's how it looks. It's better when it's written. Yes, so there's also the algebraic expression of this gate. So this gate, okay, quantum gates are also unitary matrices. They're represented as unitary matrices. And we dealt last week with the NOT gate, and it's an identity matrix. Even this one is also one of those. So it's denoted by this 1 out of root 2 times into square brackets 1, 1, 1, negative 1. Yes, so if you want to prove what happens to ket state 0 turning into this equation I showed you up here, this one, we're just going to prove that when you apply it to this state, you get this. So mathematically, this is the first bracket represents the matrix. Then that part ket 0 is the state. So when you do the math, when you deal with these square brackets first, on the right hand side, we shall get 1 out of root 2 into brackets 1, 1. After multiplying, we remember that math. So what we do, we just separate that 1, 1, and then we get 1, 0 plus 0, 1. So we know that 1, 0 represents the state 0, and 0, 1 represents the state 1. So henceforth, we have proved that applying this matrix on ket 0 gives us this equation. So that's the Hadamand gate. What can it be used for? So the Hadamand gates and other gates make it possible for computers to take shortcuts that classical computers could not have done, hence solving problems faster. Yeah, if we apply it to the state 0, we get the other equation. Then when we apply it the second time, we get back the original state. So in this diagram, we have two gates put together. So what they're telling us is that when you put these two gates together, you get a quantum wire. Yeah. So the net effect is the same as a quantum wire. This is critical for many algorithms for quantum computing. So that's the end of the Hadamand gate. Last week, the last slide, I forgot to add that also when you apply two NOT gates in one straight path, we get back the same state or the same superposition. So that's it for today, and the next one will be measuring a qubit and its measurement in computational basis. Yes, thank you.